Okay, Simpson's paradox. Let's dive in. First, I want to talk about something that isn't weird or doesn't seem weird, because when we look at Simpson's paradox, this is the thing we're thinking in the back of our head. We're comparing it to. And this thing works exactly as you would expect. It's a weighted average. Let's pretend that we can survey all the students at AU and you split them up into whatever gender categories you want so that they're non-overlapping. And for each category, like guys, women, and non-binary, they all say that they prefer chocolate over strawberry. Okay, you can then conclude that for the whole student population, that more people prefer chocolate to strawberry. Okay, that works exactly the way you expect, because the weighted average cannot be higher than the highest ratio or lower than the lowest ratio. It has to be somewhere in the middle, and that does exactly what you would expect. That is not a paradox. That's what we're thinking about in the back of our minds when we view Simpson's paradox incorrectly. And in fact, you may not necessarily think Simpson's paradox is a paradox, because if you're thinking about it properly, then you won't be tricked by it. But it's very easy to get tricked by it, and there's a collection of phenomena that work very similarly. And if you want to Google it online, there's Simpson's paradox, Lord's paradox, and just suppression effects. And so those are good search terms. So this can work with categorical or numerical data, or ordinal data, anything you like. But when you have slightly different data types, we name it the effect slightly different names. So here is a visual on what Simpson's paradox look like if you're using numerical versus numerical data. So you may fit some best fit lines. They're suggestively colored pink and blue. Maybe you're splitting into male and female. And there's a positive correlation for males between X and Y, and there's a positive correlation for females between X and Y. But if you look at the aggregate data, it seems to say that there is a negative correlation between X and Y. So that's the paradox. Now, we expect usually if for each subgroup there's a positive effect, then overall we should get a positive effect. And that's what human beings tend to think, and it works fairly often that way. But you don't want to fall into the trap of thinking that it always works that way. Again, similar effects happen regardless of the type of data. Okay, here's an example, like a thought experiment. I have often plotted things like study time against grades. I'll ask students, how much time did you study? And I'll plot their grades. So I will find that sometimes I have a class where the people who study like not that much have the higher grades. This does not mean that your grades go up if you don't study. That's just because there's some students who could bring a B+ to an A, but they don't really care. And there's students who have to work really, really hard to get a B, and they do that. So the data can hide some obvious truths if we don't look at it properly. Okay, how long has Simpson's paradox been discussed? Well, it was kind of dubbed Simpson's paradox sometime after Edward Simpson talked about it in his paper in 1951, but it had been kicking around for quite some time. You can see already been kicking around for more than 50 years when he talked about it, and it's been going strong for more than 50 years since then. So a lot of these articles I've collected for you, and they're available on Blackboard for you to look at. I hope you browse through them a little bit and get a sense for some of the things that are being discussed, even if you just read like the abstract out of a couple of them. That'll give you a flavor. But yeah, so this guy seems to get all the credit, but lots of people have been talking about it. Okay, here's a problem. We, as educators, brought Simpson's paradox into the classroom as a prime example of why we needed better quantitative literacy, or whatever you call it, numerical education, whatever buzzword you want, and we wanted to bring it into the classrooms. And we thought people needed to rely more on data instead of relying on intuition to form beliefs. That seems logical, right? But there's a problem. What we ended up with was an artificial treatment of the subject, with most of the examples that are given to the students as only explaining this phenomenon of lurking variables. So we basically say, hey, if you split the data properly and find the lurking variable, you can get rid of the effect. Well, lurking variables are quite important to be sure, but they only tell one part of the story. Some of you may be saying, what's a lurking variable again? Well, it's part of your model or explanation which is crucial yet missing. It's something that really helps you understand what's going on, but you've somehow overlooked it. Like in our previous example, maybe we overlooked gender when we did our best line fit and we concluded we had a negative correlation instead of saying, hey, but if you split by gender, we have positive correlations. Okay, so the point is your understanding of the situation is fundamentally broken because you overlooked an important part of the analysis, unbeknownst to you. Okay, but with the push to add Simpson's paradox to standard classroom fare, most treatments of it overlook its main point. The data do not tell you whether you need to look at the aggregate or the grouped data. Even if you find that special variable to split on and you find this phenomenon, you have to look at the situation, you have to understand the context in order for you as the human to decide whether it's the aggregate data or the group data that are important to the analysis. That's intuition. Here I will review the two examples given by Simpson himself, and some may complain that, oh, this is a contrived example. Well, that's just the point. So if you can come up with a contrived example, it's demonstrating that this effect can be alive and well in your real data. Notice that what he gives is identical data, the self-same data for two different problems, and all he does is changes the context of the numbers. And then he comes to a different conclusion based on the context, not based on the numbers. Also, please note the numbers are very small, but that is not to be a distraction. Yes, if you put them in and they're not statistically significant, but all you have to do is multiply everything by 1,000 and it suddenly becomes statistically significant. So keep that part of the discussion out of your mind for now, even though it's an important part of Simpson's paradox in real data. For contrived data, don't worry about the significance being a problem. Okay, so Simpson calls this part, baby plays with cards. Okay? An investigator, like a researcher, wishes to examine whether in a pack of cards, the proportion of court cards, that's just Jack, Queen, King, whether it's associated with color, which is red or black. Now, you guys who have played with cards, which are most of you, know that it's exactly proportional, right? So whether you have red cards or black cards, you have exactly the same ratio of Jack, Queen, King in both colors. Okay, so we know that, and his reader knows that. So we know right away that there's something funky going on. Okay, it happened that the pack which he examined was the one which baby had been playing with, and some of the cards were dirty. So he assumes that dirty means the child likes the cards more because they've been choosing to play with them. So he included classification dirty in his scheme in case it was relevant. So you see, he's trying to see if there's more Jack, Queen, King on the dirty cards, or comparing Jack, Queen, King versus non-Jack, Queen, King, which he calls plain, and he splits it up into dirty and clean just in case it matters. Okay, it will be observed that baby preferred red cards to black cards and court cards to plain. Okay, big deal. Okay, but here's the crazy part. Of course, if you add them all together, you get exactly the ratios we said we would. But the point is, he's saying when you do split it by dirty and clean, you get this positive association between red and plain. So what we're saying is, if you take, hopefully you can see this mouse, if you take the expected value of red and plain for dirty cards, you should only get 7.8 plain red dirty cards, but you actually get 8, so you get more than expected. But the same exact thing happens on the clean cards. If you work out the numbers, you should only get 11.81 plain red clean cards, but you get 12. And what happens with this two-way table is if there's an association between red and plain, there's also an association between black and court. Okay, so those are complementary. They're not opposites. They're the same effect. Okay, so you have higher than expected number of black court cards when they're dirty, and you have higher than expected number of black court cards when they're clean, and also red plain. Okay, so that's just weird. Okay, so now we take the same exact No, so what he said is obviously you have to look at the combined data in order to make sense that even though this effect was prominent, if you look at all the data, the red and black cards for court versus plain, it's clear that there's no association, okay? All right, and the same exact data, he now has a different question. He says, suppose we change the names of the table thus. The probabilities are the same. There's the same degree of positive association in each of the 2x2 tables. This time we say there's a positive association between treatment and survival for both males and females. But if we combine the tables, we again find there's no association between treatment and survival in the combined population. What is the sensible interpretation here? The treatment can hardly be rejected as valueless to humankind when it is beneficial when applied to both males and females. So he says in this case, if you're talking about treatment for a disease, and for males the treatment helps, and for females the treatment helps, then with the same exact data you can't throw out the results, because now the aggregate data is not very useful, but the split data is what you need to look at. So wait, how did that happen anyway? Our two-way table was really one main two-way table, which was split up again into subcategories. So you really have three-dimensional data. In this case, we have 8 possible combinations. You can be male or female, dead or alive, treated or untreated. So, or you could be, for the cards, you could be black or red, court or plain, dirty or clean. So in each case, you have three possible axes, so to speak. And just to make everything easy, everything's binary. But it doesn't have to be binary, but it's just easier to understand the examples when we do it that way. When we have three-dimensional data, we can fall into this trap of comparing only one part of the data without seeing it in the context of the whole properly. So for example, we go back to our original example with the strawberry and chocolate. This wasn't a problem because we didn't have 3 variables interacting. We just had the flavor of the ice cream versus the gender of the student. So there were only 2 variables and we couldn't fall into this trap. But we can fall into this trap because we actually have three-dimensional data and we're just smashing it inappropriately. Okay, so here's another example. I made this one up. It's completely bogus. Okay, so in this two-way table, we are shown that about 25% of Slytherin students end up getting detention, while about 31% of Gryffindor students do. But Gryffindor students complain that they tend to be the more well-behaved students. Okay, so what if you split it up between younger and older students? If I look at the younger students, the Slytherins have 50-50 chance of having had detention, where the Gryffindors, only about 1/3 of the younger Gryffindors go to detention. But then as they get older, let's say that they learn how to evade detection, or maybe they become better behaved. So for the older students, about 5% of Gryffindor students end up in detention compared to 14% of Slytherin. So for both age groups, Gryffindor has less detention. But the issue here is that most Gryffindor students are younger and most of the Slytherin students are older. So it's not fair to compare these kids without considering that ages are nowhere near proportional. Okay, here's one of my favorite examples. The internet abounds with awesome examples. You can just Google this and watch the YouTube videos and stuff. This is really amusing. So here's Simpson's paradox with Alice and Bob. Alice and Bob are fruit sellers. Alice has 3 apples, 2 of which are bad. Bob has 100 apples, half of which are bad. And he has 3 perfectly good bananas. Whereas Alice has 100 bananas, only 3 of which are bad. Okay? So if you know you have to buy an apple, you should go to Bob. If you know you have to buy a banana, you should go to Bob. But if you just want to buy a random piece of fruit, and you don't care, you should just go to Alice, because Alice has better fruit overall, but even though her apples are worse and her bananas are worse. Make sense? Okay, so here's another example. This is a classic, and I don't have the numbers for this but it's real data. This is for real. Okay, so babies who are born to non-smokers, there's more underweight, there's a greater chance, I think, a greater probability of being underweight if you're born to a non-smoker, or something like that. I don't remember the exact thing, but a superficial understanding of it would lead you to believe that you should smoke in order to avoid having an underweight baby, which is completely ridiculous. Anyway, I think it's, yeah, survival rate. Okay, survival rate for underweight babies versus survival rate for normal babies. So if you're a non-smoker or smoker, the survival rate for above a normal weight babies is the same, but for underweight babies, if you're going to have an underweight baby and you're a smoker, this baby has like a better chance of survival, something like that. Anyway, you can go look at the numbers, but it's really shocking. But it does not imply that you should start smoking in order to protect your baby. That's ridiculous. Okay, here's another common example. We have two players. So Williams and Durant is a common example brought up in statistics class. So in 2015, Williams had a better average than Durant, and again in 2016. But Durant had the better overall average because you have to not just look at the ratio, but you have to look at the fact that, look, Durant had so many more opportunities. So like even though his averages were lower each time, look at this huge amount of success. It kind of, it balances out for the fact that Williams didn't have as many opportunities. Okay, so this flip can happen at multiple levels. The following has to be fabricated data. It's completely bogus, but you can see how it could happen. Okay, I reversed the order of these slides. Let me just show you these slides. Okay, so initially, if in math and English, this fake admissions data, they let in 70% of the women and 50% of the men in math. They let in 5% of the men in English and 7% of the women in, yeah, what the chart says here. So, so this guy is claiming reverse sexism. But if you look at the aggregate data, men are admitted more than women. Okay, so if you look at the aggregate data, men are admitted more than women. When you split by discipline, women are admitted more than men. Okay, so the point is this is actually based on historical data, but these are bogus numbers made to reflect the historical story. Okay, I think it was Berkeley or something out in California. Okay, so then what these people did is they made up an example where there's reverse discrimination twice. Okay, so men are admitted more than women, but by department, women are admitted more than men. Then if you split again by whether they're blonde or not, then men are admitted more. So more, if you're a blonde man, you're admitted to math more commonly than a blonde woman. And if you're a blonde man, you're admitted to English more than if you're a blonde woman. And that's just completely ridiculous, but it's completely contrived data. Okay, so you get to work on these various things in your worksheet. So have fun with that.